Welcome to Introduction to Optomechanical Design, the short version. What I'm going to be doing in the next 30 to 40 minutes is giving you a brief overview of the course and a flavor for the course. You will note that there are two names on my course notes, my name and my dear wife's name. I've been teaching this class for a long time. I started in 1985, and at that time I used a methodology which you may have seen in museums called old-fashioned transparencies. I made these transparencies from penciled notes. My dear wife thought this was highly unprofessional, so she converted it to a computer format, which we've continued to upgrade as time has gone by. She's done enough work on the notes by this time that I've listed her as a co-author. Now, one of the issues that always comes up with this class is my long last name. People are always afraid to ask questions because they are afraid that they will have a problem pronouncing my last name. I have heard a lot of variations on Vukobratovich over the years. That said, it is not necessary to pronounce my last name to ask a question. If you have a concern or question, please ask it. The whole point of this webinar is to present information, and if you're not getting it, we need to know. Or if you have a question on the content, we need to know. So please don't be shy about asking questions. Keep in mind that we have a limited amount of time available. I may not be able to answer all your questions in the time that we have available. The next slide, Sherry, is the agenda for the course. I'm going to give an introduction, a course outline, then I'm going to give you an example of the technical content. So we're going to get hot and heavy into technical content, and then I will finish up with the summary. This will give you a flavor of what the course is all about. The next slide is an introduction to the course. I am, of course, Daniel Vukobratovich. The purpose of this course is to give you introductory material on optomechanics. I have a simple philosophy concerning teaching this course. This is all the stuff I would have wanted to know when I first started out in optomechanics. If somebody could have handed me this course or my course notes, that would have been a real boon. I can sort of make a joke about this. There's a classic Mel Brooks comedy movie called Young Frankenstein. And the very first scene in the movie shows the set of bony hands holding this book, which if you look carefully is titled How I Did It. I've always wanted this book, but only the version for optomechanics. So this course is my attempt to provide that book. It's a 16-hour course. Actually, it ends up being 18 hours because we have a 1-hour lunch break. So you're going to be listening to me talk about optomechanics for 2 days. Who should be taking this course? Well, if you're a mechanical engineer and you're going to be working with optical systems, you need this course. If you're an optical engineer, you need this course. An optical designer needs this course. Believe it or not, somebody has to wrap metal around those wonderful lens designs you come up with. And program managers may want to take this course to understand a little bit more about what's going on from the standpoint of optomechanics. Now, you do need a few things to be able to take this course. You need a little knowledge of optics and mechanical engineering, college level math. However, you don't need calculus and you don't need differential equations. If you understand algebra, you can take this course. The next slide is an outline of the course. Basically, the course is divided into 4 sections. We spend a good bit of time talking about material properties and figures of merit. This is really important in optomechanics. And we'll be talking about some interesting topics here, including the strength of glass and dimensional instability. Then we talk about general optomechanics. The things that are really important in this area are kinematics, a very interesting philosophy of mechanical and structural design. How do we make systems that are insensitive to changes in temperature? How do we deal with vibration? Vibration is everywhere. And sooner or later, if you work in optomechanics, you will have to deal with vibration. And of course, one of the things we have to deal with is precision motion adjustment. When the Optomechanical Working Group was founded, way back when. Roger Rees, one of the founders, made the comment that the success or failure of an optomechanical system depends upon the quality of its adjustments. This may be an exaggeration, but it's not much of an exaggeration. Then we're going to talk at great length about lens mounting. I present a technique for analyzing the interaction of a lens mount with the lens. This is a very conservative technique. If you design a lens mount using this technique, you can have high confidence that it will perform correctly. This is something we did not have when I first started teaching this course back in 1985. But now we have a methodology for designing a lens mount, which allows us to analyze that interaction. I'm going to be talking about this at great length. And finally, I'll finish up by talking about how we mount mirrors, both small and large mirrors. The next slide talks about what Optomechanics is all about. You're taking this webinar, and hopefully you'll be taking the course, and people are going to ask you, well, what are you doing? And you're going to be saying, well, I'm studying Optomechanics. And the next question is, what is Optomechanics? Well, if you think a little bit about it, everything we do in optical engineering involves the interaction of light with the surface. We're trying to control the light. It follows then that optomechanics is all about maintaining the correct shape and position of the surfaces of an optical system. It's as simple as that. We're trying to keep those surfaces in their correct shape and position, regardless of the surface environment, temperature, vibration, and so forth. So that's a little bit like saying that civil engineering is about designing structures that are in static equilibrium, but it's a good philosophical start for optomechanics. There's a famous quote from Jacobs made way back in 1943. He wrote a book on optical engineering, which is mostly about optomechanics. And what he said starting out was, in the design of any optical instrument, optical and mechanical considerations are not separate entities to be dealt with by different individuals, but are merely two phases of a single problem. This is exactly correct. Mechanics and optics have to be integrated. Arguably, when Galileo designed his first telescope, optomechanics was created. Believe it or not, I go back a long way, but I did not help Galileo. I want to make that very clear. The next slide shows a little bit of a flavor of this course. I'm going to be talking now very technically, and the topic I'm going to be talking about is the use of adhesive bonding in optomechanics. This is a topic that always seems to generate a lot of interest when I teach optomechanics. So for the next 15 minutes or so, I'm going to be talking about adhesive bonding, and I'm going to be talking about this at a fairly technical level to give you a flavor of how the course is organized and what sort of material you would be exposed to. So let's talk about adhesive bonding. Adhesive bonding is a very common methodology in optomechanics. Now, when we start talking about adhesive bonding, there are three concerns we've got. One is stiffness of the bond. Another, and this is one we'll talk about at considerable length, is stress due to different thermal coefficients of expansion. Invariably, the adhesive is bonding glass to metal, and the glass and metal have different thermal coefficients of expansion. Also, we have to worry about possible contamination. This is something that's actually fairly easy to take care of, and I'll mention that in just a moment. Now, when we talk about stiffness, we have to realize that even a stiff epoxy is not nearly as stiff as metal or glass. As a very rough rule of thumb, the elastic modulus of most adhesives is about 1% of that of the materials we use in optomechanics. So when you start thinking about adhesives, they are not really structural materials. They are more like springs. So think about an adhesive as a kind of spring. Now, another concern with adhesives, in addition to their low stiffness, is their very high thermal coefficient of expansion. The thermal coefficient of expansion of some adhesives can be as high as 200 parts per million per degree Kelvin. And by the way, I'm an engineering physicist, so I tend to talk about temperature in terms of degrees Kelvin. Not a big deal. Kelvin is equivalent to centigrade. For those of you who are not yet metrified, the conversion factor is 1.8. But this is an additional issue. Now, it turns out, as we will see, that this very high thermal coefficient of expansion is offset by the very low stiffness of the adhesives. That works out pretty well. Generally speaking, when we select an adhesive, we try to select an adhesive that satisfies the NASA requirements for outgassing. This means the adhesive has less than 1% total mass loss and about 0.1% collective volatile condensable material, or CVCM. This is based on the ASTM test. Now, this is not something you need to worry about a whole lot. The government of the US has provided us a wonderful resource in the form of an outgassing website, which I've listed here, outgassingnasa.gov, which has a lot of adhesives. So you can go through that list of adhesives, find one that has the particular properties that you're looking for, make sure it meets this criteria, and you're good to go. If your particular adhesive is not listed in the NASA database, I would suggest you should not use it because it's not properly characterized. There are a lot of adhesives in that database. The next slide talks about the generic applications for adhesive bonding. When we talk about adhesive bonding, we generally have 3 different applications. Probably the most important from the standpoint of optical design is optical bonding. When we put together a lens assembly, a doublet or triplet, the lenses are held together by means of a very thin bond line of a high transmission optical adhesive. The next application that's very important is actually using the adhesive to hold the lens to a mount, metal to glass. Here we want a low outgassing adhesive so we don't have contamination of our optical surface. We want to have high flexibility after curing to take out the difference in thermal coefficient of expansion between the mount and the lens. Last but not least is structural. In some cases, we may take the mounted optic in its mount and bond it to a chassis or barrel. In this particular case, we want a high stiffness and high strength adhesive. Typically, we would use an epoxy for this application. Now, because of the high thermal coefficient of expansion of the adhesive, we need to be very careful about the geometry of the adhesive bond. It needs to be symmetrical. If it is symmetrical, when we have a change in temperature, assuming we don't have a gradient, we don't see a shift in position of the optic. Again, we are trying to maintain shape and position. So we need to be very careful about symmetry. We also need to make sure that if we have a series of spot bonds, that all the spot bonds have the same thickness, at least to some tolerance. The next slide shows the types of adhesives that we use. I'm going to move fairly quickly through this. Epoxies are very commonly used. They offer high strength and stiffness. Polyurethanes have fallen out of favor today, so I'm not going to talk too much about those. The RTVs are very common. They're used a lot. They have the advantage of being very flexible. The UV cured acrylics get used a lot. These materials have the advantage of being cured almost instantaneously. This overcomes the classical pot life problem in working with most adhesives. Now, you have to be careful with UV curing adhesives. People on the production floor, people in the factory like to use a big blast of ultraviolet to cure the adhesive right now. That is not good design practice. The reason it is not is the faster you cure the adhesive, the more shrinkage and residual stress you will see in the bond, which may cause the bond to fail or the optic to move out of position. For this reason, it is very desirable to prolong the cure. One approach that you can use is to use a brief blast of UV to essentially tack the material in place so you can handle it. And then you can put the optic in what is called a UV curing cabinet. This is simply a box with UV reflecting interior walls with a flood UV source and cure the adhesive over a period of hours. This reduces the shrinkage and residual strength and is greatly preferred from the standpoint of ensuring that you have good long-term stability of your optics. Now, I'd like to mention the cyan acrylics. These are mostly used as thread lockers, and People tend not to think too hard about these because they're a thread locking material. Many of these cyanocrylic thread lockers outgas massively. The outgassing can attack and stain an optical surface. So cyanocrylics should be kept well away from optics. They are good materials. I'm not knocking the use of cyanocrylic thread lockers. It's just you want to keep them away from your optics. The next slide is just a brief table of the different types of adhesives that you might want to use in Optomechanics. I apologize if your favorite adhesive isn't in this table. It's here mostly for tutorial purposes, as is the table in the next slide, which again shows some properties of representative elastomeric sealants. Again, I'm not going to dwell too much on this. This is just here for tutorial purposes to give you some flavor for the properties of representative adhesives. The next slide. All right. In this slide, we're going to discuss how you go about engineering an adhesive bond. An adhesive bond needs to be engineered just as carefully as any other part of a optomechanical or structural system. Basically, you start the design of an adhesive bond by figuring out how much area you need. The area of the adhesive bond is going to be dictated by the mass of the thing you're trying to hold in place, by the specified acceleration. Now, for a laboratory environment, that could be relatively low. However, note that if you have a suddenly applied load, you can see 2 G's of acceleration. If you had a safety factor of 2, you could easily end up with 4 G's. So even a, quote, laboratory instrument, unquote, should be designed to handle around 4 G's of acceleration. Many applications require much higher levels. Very common standard today is 75 G's. That's a lot, but people design to it. Note that you need to know the adhesive strength to do this. So this tells you the size of the adhesive bond. Okay, fine. How are you going to apply that? Well, you've got a little bit of a problem. I'll come to that shortly. And that problem is that if the adhesive bond area gets too big, you may have excessive thermal stresses. In this case, the appropriate response is to break up the bond area into a series of smaller bonds. So typically what you'll do is say, okay, the maximum bond area I can tolerate without having excessive stress is this number. You will divide that into the total bond area, and that will tell you the number of bonds you need. We call these small bond areas spot bonds. Now, as I've mentioned, the bond area is influenced by the thermal coefficients of expansion of the materials. The next slide shows how we go about deriving the maximum size of the bond area. Basically, the maximum size of the bond area is set by the shear stress in the adhesive. So here we see an equation which allows us to evaluate that shear stress. I'll walk very quickly through the elements of this equation. Alpha sub 1 and alpha sub 2 are the thermal coefficients of expansion of the metal and glass that we're bonding together. Delta T is the change in temperature. G is the shear modulus of the adhesive. L is the maximum size of the adhesive bond. Now here you have to be very careful. L would be the diameter of a circular bond. But if you're using a rectangular bond, this is the longest length of the rectangular bond, and that would be the diagonal, not the side, but the diagonal, longest length. H sub r is the thickness of the bond. We can see that the thicker the bond, the lower the shear stress. Beta is a parameter which incorporates the shear stress of the adhesive, the thickness of the adhesive bond, and the stiffness of the two things we're sticking together, E sub 1 and E sub 2 being their elastic moduli, H sub 1 and H sub 2 being their thicknesses. Note that beta has units of inverse length. Now, this equation requires the evaluation of a hyperbolic tangent. Not a big deal if you're using a pocket calculator or a modern program like Mathematica or MathCAD. So you shouldn't be too frightened by that hyperbolic tangent. Typically what we will do, knowing the shear strength of the adhesive, is use this equation to solve for L. That in turn will dictate the size of the bond, and then we can derive perhaps a series of spot bonds. Now you'll notice down at the bottom a thing that says bibliographical references. I can't teach you everything I'd like to teach you in 16 hours. I teach this class at the university. I teach it for a full semester. I still can't teach what I'd like to. So what I've done is provide a very large bibliography at the back end of the course. This bibliography has been called, not by me, the most extensive one in optomechanics. We can argue about that, but it is pretty comprehensive. I update it continuously. The next slide is simply a discussion of the stability of bonds over temperature. Basically, we have to have symmetrical bonds. Let's suppose that we were doing something like gluing down a mirror, and say that we've done our spot bond equation. We said, okay, I'm going to use 3 spot bonds. That's a perfectly acceptable approach, except we have to be careful to make sure that all 3 of the spot bonds have the same thickness. We can assign a tolerance to that. We cannot, of course, make them exactly the same thickness, so we have to have some tolerance. The way we can do that is knowing the tolerance on the allowable tilt of the mirror, delta theta, in radian units, knowing the thermal expansion of the adhesive and the change in temperature, delta T, we can then derive delta H sub R, which is the tolerance in terms of thickness from adhesive bond to adhesive bond. So this allows us to ensure that we will have good stability over temperature. The next slide shows a technique called liquid pinning. This is a way for making a lockable adjustment. One of the problems with adjustments is they tend to move out of position. It's very common when you're working with optical devices to be doing a series of adjustments. Very tedious process, can take a long time. You finish up at the end of the day, you go home, come in the next morning, things have moved. Nobody will own up to adjusting your system. So obviously you've been struck with the midnight knob tweaker, the person who comes in the middle of the night and makes your adjustments. Well, if we use a liquid pin connection, that problem goes away. Here we see an example of a liquid pin connection. We have an optic in a mount. This is a tutorial example, so it's not too terribly realistic, but the mount has 2 oversized holes. Those oversized holes go over some pins. This allows us to move the mount around relative to the fixed pins. When we are happy with the position of the optic, we then insert an adhesive around the circumference of the fixed pin, typically a high stiffness epoxy, and then this locks the mount to the structure. It's a very stiff type of adjustment. It can be reworked. We can use a hollow core drill, which can be slipped over the fixed pin to remove the adhesive, take the thing apart, remount the hole, and start all over again. So this is something we can rework if we wish. The general rule of thumb, by the way, when you work with adhesives is be sure before cementing. You can usually take an adhesive mount apart, but it can be, shall we say, somewhat challenging. The next slide shows the engineering part of a liquid pin connection. I've just shown you in a schematic form how you do it. Now let's get down to the nitty-gritty of how we would design a liquid pin connection. Obviously, when we design such a connection, we are concerned about its stiffness. K sub R. There is a radial springs to rate. Interestingly enough, that spring rate does not change even when the pin is decentered. I don't have time in this webinar to talk about that, but it can be shown that even if the pin is decentered, the spring rate remains constant. In this equation, we see that there are a couple of terms that are very important. One, of course, is the diameter d sub p of the fixed pin. Another is the length of engagement of the adhesive, L sub p, in contact with the pin. R sub R is the average radial thickness of the adhesive around the pin. That is simply the diameter of the hole minus the diameter of the pin divided through by 2. The term in brackets has to do with the elastic properties of the adhesive. Its elastic modulus, its Poisson's ratio, and its shear modulus. Generally speaking, these properties are not well understood. Typically for an adhesive, even a well-characterized adhesive, We may not know the elastic modulus to an accuracy of much better than 10%, and usually Poisson's ratio is not known very well at all. For most epoxy type adhesives, Poisson's ratio will be about 0.43. I'll talk about that more in a little bit. The next slide shows how we would implement this in an actual application. You can see we've got a lens and a mount. We've got a ring of liquid pin connections. We shift the lens mount around to center the lens. When we're happy, we add the adhesive and lock the whole thing together. The stiffness of this is simply equivalent to N/2 times the stiffness of a single liquid pin connection, where N is the number of equally spaced liquid pins. You can use as many as you want. I've mounted large lens assemblies with as many as 18 liquid pin connections. So you can get almost any arbitrary level of stiffness you want with this methodology. The next slide shows some details you need to be concerned about. There's an old saying, the devil's in the details. That's very important in optomechanics. If the adhesive is allowed to flow up over the top of the surface and you have a drop in temperature, that can produce a tensile stress on the corner of the optic, which can lead to a fracture. For that reason, the adhesive should be below the edge of the adhesive of the edge of the lens, as I've shown in the lower illustration. It's very common to use injection holes to inject adhesive around the circumference of the optic. Good idea, except if you leave the adhesive in the injection hole and you have a drop in temperature, the thermal coefficient of expansion of the adhesive being very high can produce a large tensile stress directly below the injection hole, which can cause a fracture in the glass, which is shown in the next slide. This is not a matter of academic concern. Here we can see where injection holes have produced fractures in a zinc selenide mounted optic. This is taken from an SBA paper by Lehay and Magner, Athermal mounting of optics in metallic housings. You can use the SBA digital library to look it up to see, yeah, this really is a problem. It's not a big deal. After the adhesive sets up, you can run a drill down into the injection hole to remove the adhesive. The next slide. This is one of my favorites. The very first SBA conference I attended was back in 1981. And Meet Bayer gave a classic paper on optomechanical design. It was short, but it incorporated a lot of good design approaches and information. This is probably, in my humble opinion, the best paper that's ever been published in optomechanics. One of the things that Meet talked about was the idea of an athermal lens mount. He said adhesives expand and contract a lot in comparison with glass and metal. Let's make that work for us rather than against us. By sizing the adhesive bond correctly, you can ensure that the bond expands or contracts the right amount during change in temperature so that it always stays in contact with the cell and the lens. This is called an athermal lens bond. He gave a simple equation for the athermal lens bond. This got people very excited, and people went off and started doing this. It was a big contribution to the community, and we've been doing this now for over 40 years. Now, typically the thickness of the adhesive bond you end up with using this approach is larger than most people are used to. This is simply because we are using adhesive as an element in an athermalization scheme. Note that we have to accurately center up the lens with respect to the lens cell before we inject adhesive. We, of course, want to make sure that the adhesive is stable and low in outgassing. The next slide talks about what's happened since 1981. Bayer's equation is very simple. And many people said this equation isn't accurate because it doesn't include a correction for Poisson effects in the adhesive. Now, this turns out to be a very difficult problem in optomechanics. How do you assess Poisson effects in the adhesive? There are a couple of issues, one of which is we don't know Poisson's ratio with accuracy. Typically for the epoxies, it's about 0.43. For the RTVs, it's probably around 0.49. No adhesive acts like a rubbery material with a Poisson's ratio of exactly 0.5. Generally speaking, if you want to use an approximation, I suggest using a value of 0.45. Now, there are a host of equations which purport to provide a correction factor for Poisson effects. Probably one of the most useful is the equation I've given you below. I will massacre the name, the Van Vejusian equation. This does include a correction for the Poisson's ratio of the adhesive. As I've said, unfortunately, we don't know that ratio with great accuracy. Now, what we can do, and this is shown in the next slide, next slide, please. There we go. Is an approach developed by Herbert. And what Herbert's approach does is allow us to calculate the stress in the adhesive as a function of the temperature change delta T. This is actually a relatively simple equation to work with. I'll run through the parameters in it. E sub r is again the elastic modulus of the adhesive. Nu sub r is Poisson's ratio of the adhesive. H sub r is the radial thickness of the adhesive. Note that in this equation, if we have a negative value that indicates a compressive stress in the adhesive, a positive a tensile. You can solve this equation for 0 to give you a quote optimum athermal bond line. Note that this stress is almost always extremely low. Now, one of the questions I always ask whenever somebody gives a paper on a better approach for designing an athermal bond line is, excuse me, we've been using Bayer's basic methodology for 40 years with really good success. So if you're going to propose a more complex methodology, please explain to me why Bayer's simple equation works so well. This usually upsets people at technical meetings, but it's a very valid thing to ask. Bayer's simple equation works quite well. The next slide shows what happens when we mount a lens using a thick layer of adhesive. Here we see a lens with gravity acting normal to its optical axis. The adhesive has a low stiffness. So the adhesive below the lens gets compressed, the adhesive above the lens is extended, and the lens moves out of position. Well, how much does it move out of position? The equation for the shift in the position of the lens is given here. W sub g is the weight of the lens, or if you wish, that's acceleration the lens is subjected to times its mass. D sub g is the diameter of the lens. H sub g is the length of adhesive in contact with the edge of the lens. Almost always that will be the edge thickness of the lens. H sub r is the radial bond thickness of the adhesive, designed using Bayer's equation, Herbert's approach, whatever. And the term in brackets we've seen before. This has to do with the stiffness of the adhesive. Now, is this a big deal? And the answer is not really. If you have a very large lens, say 1/4 meter in diameter, 10 inches for those of you who are not metrified, with a very thick bond line, say a radial bond line thickness of about 6 millimeters, about 1/4 inch, using an extremely flexible adhesive like Dow Corning 93500, the lens will only decenter on the order of 2.5 to 5 microns, a couple of 10,000ths of an inch. So typically speaking, even with a very soft adhesive in RTV, decentering is not an issue. However, this equation does allow you to predict that. The next slide summarizes what we've talked about. So my course emphasis is going to be on understanding optomechanical problems and using closed form analysis. As you've seen, the equations lend themselves to analysis using a spreadsheet like Excel, Mathematica, MathCAD. I have provided details on a variety of solutions. As you've seen, I've given you design equations. At the back of the course notes, you'll find I've provided worked examples. There is a very extensive bibliography. My apologies for boasting a bit about that. The notes are intended for use as a desk reference. I have been teaching this class since 1985, and I find that my course notes have proliferated like rabbits. I will visit a company and somebody says, "Oh, Dan Vukobrowicz, I have a copy of your your course notes. I said, really? Have you taken the course? Well, no, but, a friend passed me a copy of your notes. They have proliferated like rabbits. I would strongly suggest that if you're going to be using the notes as a desk reference, you probably should take the course as well. Now, for what it's worth, I've been teaching this course since 1985. I've presented for the Society for over 100 times in 12 different countries. We've been very successful with good evaluations, but there's always a first time. So generally speaking, if you want to learn about optomechanics, this is a good way to do it. You get a lot of information in a very short period of time. The biggest complaint I hear about this course is it's a lot of information in 16 hours. I'd rather give you too much than too little. And with that, let's go to questions and answers.
Thank you so much, Dan, for that fantastic presentation and all that information. So we have about 20 minutes left in the webinar. I don't see any questions in our Q&A quite yet. So as Dan said, please don't be shy. Please do ask your questions. This is a wonderful opportunity to ask an expert. Let's see if we've got any in here. Dan, if we don't have any in, do you have any questions maybe that are common questions that folks ask you in your class?
Okay, well, one very common question I get asked, of course, is about which adhesive to use. Unfortunately, the SBA says I can't make product recommendations. I can talk generically about adhesives, but I can't say, well, go out and use company XYZ's products. I will generally say that for most lens mounting applications, we will use a semi-flexible adhesive, an elastomeric adhesive like an RTV. There are a wide variety of such RTVs available. The table I presented gives you some samples. Of course, the NASA outgassing site has a bunch more. So generally speaking, we will be using a adhesive which will be selected because it's semi-flexible. So I can't really get into the details or the nitty-gritty, so to speak, of which product you should use. After the course, and I'm not on the SBA clock, we can talk about that. I saw a question about plastic optics and mounting, and the answer is absolutely. I have a section in the course notes that talks about the problem of plastic optics. Plastic optics are really important. Whenever I teach this class, when I start the section on plastic optics, I say that people have an aversion to using plastics. And the reason they have this aversion is, oh, plastics, they're not really good. And then I say, well, everybody here probably has a plastic optic. And people say, what do you mean? I say, it's your cell phone camera. Most cell phone cameras use plastic lenses. They work fantastically. The modern ones especially have awesome capabilities. So before you start poor mouthing plastic optics, take a look at your cell phone camera. This is a very important area of optomechanical design. As I like to tell younger engineers, cost is an engineering variable, and plastic optics address this. I got another question about structural analysis and optomechanics. Why are we talking about structures? Well, again, we are trying to maintain the correct shape and position of our optics. That involves structural analysis. So when we start thinking about a lens, for example, we want the lens to hold its shape and position. Well, we have to be able to model the effect of the mount on the lens. And we find that if we're not careful, the lens mount can distort the lens. This will make the optical designer quite cross, because if the surface of the lens is distorted, the lens will not perform properly. Generally speaking, we cannot hold the lens in a zero stress condition. Every time we touch the lens, we put some stress into it. For that reason, we have to have a tolerance associated with the allowable deformation of the lens and the stress that goes into the lens. And then we will design the lens mount to accommodate that tolerance. So structural analysis is very important in optomechanics. Any other questions we might have? I see the chat is filling up.
Dan, we have some questions in the Q&A here that I'm going to read off to you here, so those don't get missed. There's a question here. What is the biggest source of failure you see from mounted optics? Thermal stress damaging the optics, demounting of the optic?
The question is, what's the biggest failure I see? And the answer is there's sort of a twofold approach to talking about failures. First of all, it's not uncommon to see failures when people are first getting involved in mounting of lenses. If you don't have a lot of experience in working with mounting lenses, you will have failures. I could mention several anecdotes about that, but I'd like to go on to mention the other source of errors in mounting or failures in mounting, and that's almost always a change in temperature. If we have a radical change in temperature, we can put enough stress in the glass that we may actually fracture the glass, infrared material, or what may you have. So thermal failures are really common. As I said, the other failure is simply learning how to do this particular type of assembly. And hopefully, if you've taken my class, you won't have that experience. I'm not really very smart, but I have a lot of Band-Aids on my hindquarters. And what I'm trying to do is transfer information to you so you won't need quite so many Band-Aids.
Thanks, Dan. I have another question here from Carlos. Asking about tolerances. What about tolerances? Is there any part of the course including measurement methods?
The question is, do we talk about measurement methods? That's really a metrology issue, which is outside the scope of this course. There are some very good courses you can take about optical metrology. That said, I do mention tolerances in the course. I have a discussion when we talk about lens mounting, when I talk about the tolerances that are normally applied to lenses and the tolerances that are applied to lens mounts. In addition to that, I introduced the concept of the stress optic effect in glass. This is another tolerance which is very important, which is often overlooked by optical designers and optomechanical designers as well. However, understanding this tolerance is the key to designing an effective lens mount. And I talk about this at considerable length in the course. So yes, we will be talking about tolerances. One comment I would like to make is that, as I've said earlier, cost is an engineering variable. We all have to worry about how much our assemblies cost, and cost usually goes as the inverse of the tolerance. So if you make the tolerance tighter by a factor of 2, you may drive up the cost by a factor of 2 as well. This relationship is not quite correct, but it's close. So you want to be very careful when you apply tolerances to ensure that you don't end up with a design that performs well, but is not affordable. So there is a relationship between tolerance and cost. Other questions?
Let's see any other technical questions in here. There's a question about optomechanical analysis. Sally, I'm sorry if I'm mispronouncing your names, but they're new to optomechanical analysis and was wondering if there are any suggestions for any sources. I know that we have the optomechanical analysis course by
Let's talk about analysis of an optomechanical system. Generally speaking, when you do optomechanics, you work a problem in a series of phases. The first thing that happens is the optical designer will show you an optical design. There will be a tolerances associated with that design. You will know the environment, hopefully, that the system is going to be working in, and you'll come up with a conceptual design or designs which may solve the problem. I provide the tools in my course to go from the conceptual design to an actual engineering design. My approach is sufficient that if you apply a safety margin to the design, which is good practice in engineering, you have a high confidence of the design succeeding. However, there are more advanced tools which are available. And the third phase of an optomechanical design usually involves applying computer-assisted design, CAD, finite element analysis, and so forth, to model the performance of the optomechanical system. That is outside the scope of my course. There are some very good courses offered. One of the leading experts in this field who also teaches is Keith Doyle. Keith is a former student of mine. He's written a couple of books on optomechanical analysis, and he essentially talks about the next level up, which is the use of computer analysis of optomechanical systems. So if you really want to get smart in optomechanics, you should probably take my course and then follow it up with the course that Keith teaches. It's really good.
Thanks, Dan. Doesn't look like we have any other questions in our Q&A. Again, if anyone has any questions, this is a great opportunity to ask Dan. Oh, looks like another one came in here from Samil. Hi all, what is the common material for housing lenses?
The question is, what is the common material for housing lenses? Everybody has their favorite material. That said, it depends upon the application. If you are building a relatively low cost, high volume application, like say a cell phone camera, you might use a plastic housing. ABS plastic is a good solution. Another are the glass reinforced polycarbonates. They are used quite widely as lens housing material. The next step up from that is aluminum. Aluminum is significantly more expensive than the plastic materials. Usually you have to machine or cast aluminum housing, but it has the advantage of being relatively lightweight, relatively economical. The big drawback of aluminum is that it has a high thermal coefficient of expansion compared with most optical materials. The next step up from that is typically to go to stainless steel. Stainless steel offers the advantage of a relatively low thermal coefficient of expansion. There are some free machining stainless steels. For example, 416 is an excellent material for lens barrels. It has a low thermal coefficient of expansion. It can be magnetically fixtured for machining and has a good thermal coefficient of expansion match with most materials. The other material which we see being used more and more often for lens barrels is titanium. Titanium is sort of intermediate between aluminum and stainless steel from the standpoint of both stiffness and mass. It has a very low thermal coefficient of expansion. It's extremely resistant to corrosion. It's a very good material for lens barrels. The downside of titanium is that it is more difficult to machine than either aluminum or most stainless steels. People often talk about the cost of titanium. The cost of the raw material is not the driver, it's the machining cost. But we're seeing more and more titanium used even in consumer optics. I have seen a number of cameras, for example, made for the consumer market, which incorporate titanium components. After that, we can get into very exotic materials, but those are pretty much the most important ones. I'm sorry if I haven't mentioned your favorite. You can come back with a question and ask me about that.
Thanks, Dan. We have another question here. Would using two different adhesives be okay? For example, one adhesive for bonding, another for sealing.
The question is, can you use two different adhesives, one for bonding and one for sealing? And the answer is that's pretty common practice. You may have an optomechanical barrel where you use a certain adhesive to bond the lenses into the barrel. And then when you get to the end of the barrel, you want to seal it, make sure that water and such can't get in. And you may use a different type of adhesive for that application. Again, the adhesive should always be carefully selected from the standpoint of its performance metrics, particularly with respect to outgassing. So if you're going to be using an adhesive for sealing, make very certain that it satisfies the NASA requirements for outgassing. But no problem with using two different adhesives.
Great, thanks, Dan. We have another question here from Arthur Seibert. Are there some dedicated, is there dedicated software to employ in Optomechanics?
The question is, are there dedicated software packages for Optomechanics? And the answer is, unfortunately, no. You pretty much have to do this on your own. That said, the techniques that I teach for lens mounting lend themselves very well to evaluation using a spreadsheet. So I apologize that I can't hand you a software package where you can input the optical design and get an optomechanical design out the other end. Unfortunately, there is engineering required. That's what we get paid to do, and that's part of the process. So no, we don't have a software package. I apologize about that. There have been some attempts to develop such packages. They have not been successful.
Thanks, Dan. I have another question here from Julia McMaster, and she asked, do you prefer cone, ball, flat, or it says 3X ball? I don't know if it's 3X or 3.
I think I know what she's talking about. You are talking about a kinematic design, and the type of kinematic design I believe you're talking about is what is called a Kelvin clamp. This is where you have 3 balls or 3 circle surfaces. One goes into a cone, one goes into a V groove, and one rests at a flat. Now, in reality, this is not kinematic. Kinematic philosophy assumes that we have point contacts, and when you have a ball and a cone, you have line contact rather than point contact. That said, this is a very common way of registering components. There is a better way to do it. I discussed this in the course. Basically, we can modify the classical Kelvin clamp by using 3 V grooves. This allows us to have a symmetric configuration, which, oh, by the way, is athermalized. It's insensitive to temperature changes. It's a better way to go. So we'll be talking at considerable length about kinematics, and I will hopefully show you why a cone ball flat is not necessarily the best way to go, and you're much better off with, as you put it in your chat, the 3X ball and groove version. That is an easier thing to build, and it works pretty well.